Okay, this tutorial is on Unit 4 vectors in preparation for your quiz on the subjects of vector addition, vector resolution, and motion in two directions for vectors, velocity vectors. So the first thing that we'll review will be the tip-to-tail addition method for component vectors in order to obtain a resultant. These could be any vectors. They could be velocity, force, displacement, acceleration. And the rule for adding them in terms of tip-to-tail is to always take one vector and add it to the tail of another, like so. The resultant vector will always be from the tail of the first to the tip of the last. Make sure that you put the arrow on your resultant vector because you need to have direction in order to have a resultant vector. And then, unless you're asked to solve for it, just give it a label with an R around, with an R surrounded by a circle. In some cases, you will be asked to subtract vectors or maybe multiply vectors, but pretty much it's still the same idea. In this case, where we have 2 times that vector plus that vector minus this vector, well, the first thing I want to do is I want to take care of the sign here. Remember, whenever you subtract something, you're really just adding its opposite. So, in this case, I want to leave, change, and then make this its opposite. And I'm going to get rid of that arrow on the other side. So it's essentially the same magnitude of a vector, but just now it's in the opposite direction. So if I were to add these, it'll look like this. I'm going to flip this guy around, same magnitude, and now I'm going to take these two, and I can add them tip to tail, like so, and I'm going to need some room. So I'll add these tip to tail over there, tip to tail there, and tip to tail there. We're kind of running out of room with the stuff that we had up here. And once I've added these vectors tip to tail with each other, it will always be, again, from the tail of the first to the tip of the last. So my resultant vector should look something like this. I'll give it a label, and that's about it. In the case where you're asked to calculate component vectors, I want you to keep in mind that the whole point of this is to just take that resultant vector and resolve it or break it down into its x and y components. That is, the shadow of that resultant that is in the horizontal direction and the shadow of that resultant that is in the vertical direction. The first step to doing this, regardless of what type of vector it is, as you see we have 3 types here. We have an acceleration vector, a velocity vector, and a force vector, all of different magnitudes and in different directions. The very first thing, before you start calculating anything, I suggest, is to take each resultant and just visually break it down into its component vectors, like so, in the horizontal and in the vertical. Keep in mind that these horizontal and vertical components, by definition, must be perpendicular to each other. That is, they must be 90 degrees. So I'm going to do that for each one of these, just so I can get an idea. And there we go. Now, I will label these as components in the x and components in the y, just because I want to keep that straight in my head. So this will be the acceleration in the x direction, and this will be the acceleration in the y. This will be the velocity in the x direction, and this will be my velocity in the y. And this is my force in the x direction, and this will be my force in the y. Now, I'd like to take care of these each individually, one by one. But before I do, I want to just direct you real quick to your physics reference tables. On the very back, you'll see 2 very important equations, and they deal with vectors in different directions. Right here on the back of your reference table, you'll see that for any vector in the y direction, you can calculate it by taking the resultant vector and multiplying by the sine of the angle between them. And that only works if you have a vector like this with its angle measured between that vector and the horizontal. And likewise, you can calculate the magnitude of any x component by taking the resultant vector and multiplying by the cosine of the angle between that vector and its component. Again, it's only going to be true if your vectors are drawn similar to this, where your angle is between the horizontal and your resultant component. But getting back to these problems, I'm just going to go through and solve them. So if I want to find the x component of this, I need to realize that it is the side that is adjacent this angle. And I happen to know the hypotenuse, so if I'm looking for the adjacent and I'm given the hypotenuse, then I want to find a function, either tangent or sine or cosine, that will help me with that. I'm looking for the adjacent, and I have the hypotenuse and the angle. I think that I'm going to use this because I'm looking for the adjacent and I'm given the hypotenuse. So I use that, and it says the cosine of the angle is equal to the adjacent side, the guy that I'm looking for. In this case, it is my acceleration in the x, divided by my resultant component, which in this case is 4 meters per second squared. And if I throw in my angle, which I've been given, in this case is 50 degrees, then I can calculate the cosine of the angle of 50 degrees and then multiply it by 4 meters per second squared so that I can get this all alone. And that would give me a value of 2.57, and the units are going to be meters per second squared because we're trying to find acceleration. And I could do the same thing up here, except now I'm trying to solve for the side that is opposite my angle. So I have the opposite, and I'm looking for the opposite rather, and I have the hypotenuse. It looks like I can use sine now. Similarly, but just with a different function, it'll look like this. The sine of 50 degrees, which again I was given, is equal to the opposite side, which I'm trying to find, my acceleration in the y direction, divided by my hypotenuse, which is 4 meters per second squared again. And now if I take the sine of 50 degrees and multiply that by my resultant 4 meters per second squared, I get 3.06 meters per second squared. That's looking at it the trig way. But really, in Regents Physics, because you have those equations on your reference table, you really wouldn't need to do that. You could just take a look at your reference table and see what value it is you're trying to solve for. I'll do that with this example right here. So, if I'm trying to find my x component, I look at my reference table and I see an equation that says this. Any x component of any vector is equal to that vector's resultant times the cosine of the angle between the resultant and the horizontal, which in this case I can just plug in 12 meters per second, because that is my resultant, times the cosine of 15 degrees. And 15 cosine times 12 gives me about 11.59 meters per second. This is the same idea as what we had done for this example, except it's already arranged so that you have the resultant times the cosine of the angle. And to solve similarly for this one over here, it would be the y component, or the vertical component in this case. And my reference table tells me that that equation looks like this. The y component of any vector, even if this one is the velocity vector, is equal to its resultant times the sine of the angle between the resultant and the horizontal, which in this case, again, my resultant is 12 meters per second, but now it's the sine of 15 degrees. And if I multiply that by 12, then I get a value in the y direction of 3.11 meters per second. And the case is similar for this example, and I can leave that up to you to try to solve. Though you should get values of 20.7 newtons for your x component and 77.3 newtons for your y component. The next thing I want to hit up is dealing with vectors that are not right triangles. Remember, if you have a right triangle, you can just use the Pythagorean theorem to solve for any side of that triangle as long as you're given at least one side and one angle. But in this case, we're given a triangle that is not a right triangle, so we can't apply the Pythagorean theorem. We either have to try to use the law of cosines, or maybe easier for us, just make them right triangles. So I'm going to take this, and I can draw in the resultant without even having to calculate anything. I just know that it's already done tip to tail for me, so the resultant will look like it goes from the tail of the first to the tip of the last. And then, to make this a right triangle, what I want you to do is just see that if you were to extend this vector in that direction, you'd see that you actually do have what could be considered to be a horizontal plane. In fact, I want to try to show you that that is the case by just rotating this entire system until it's level. Now, what I can do is I can take this component right here, the 15 Newton component, and I can turn it into its own components that are purely in the x and the y directions. And I can do that by using a method similar to what I had just shown you. This angle right in here, if this is 130, and from there to there would be 180, this must be the difference, which would be a 50-degree angle. And now I want you to see you have a 15 Newton vector at 50 degrees to the horizontal, and you should be able to break that up into its components, just as we had done in the previous problem. Using those methods, you should be able to at least draw in the horizontal and vertical components of this 15 Newton vector that will make it a right triangle. So, using those methods, you find that the vertical component should be 11.5 newtons. Again, I used this equation, where the angle theta is this angle right in here, and you should find by similar methods that the horizontal component of this 15 Newton vector is 9.64 newtons. Now, what I want you to see is you have a triangle that is now a right triangle, and it has dimensions that are the same as the one drawn below, except I'm just going to draw in the completed right triangle, where you're looking for this resultant. You don't know what it is, but you now know that this leg of the triangle, the horizontal component, is the result of this plus this value. Adding those together, you should get 21.94 newtons, and the vertical component here is this value, which is 11.5 newtons. And realize that because these are a right triangle, you now can use the Pythagorean theorem. So a squared plus b squared equals c squared, but if you square root both sides, then you will get 24.8 newtons as your resultant vector. 24.8. Now, that is just the resultant vector's magnitude. What you would also need to do is determine this angle in here so that you can report its value, say, from north. And again, to do that, you would need to draw in this axis system. And what you want is this angle from north. Or if you find this angle, you can report it north of east, if that were your axis system. So to do that, now that you have all three sides of this triangle, you can just use your trigonometry functions. Pick your favorite one, tangent, sine, or cosine. All of them can be used because you know all three sides of the triangle. I'm feeling like using tangent today. So because tangent of an angle, which I'm looking for, is equal to the opposite side, 11.5, divided by the adjacent side, 21.49, then I can throw those into this equation, and I will get a value that when I second function that in my calculator, so 11.5 divided by 21.49 is 0.53, and if I hit the second function tangent in my calculator, I get an angle of 28.1 degrees. Realize that 28.1 degrees is this angle right in here. So if I am to report this value from north, it would be 90 minus 28.1 degrees. Or I could just report it north of east as 28.1 degrees. I'll do that. So my final answer for this one, in terms of the resultant and its direction, would be a magnitude of 28.4 newtons at a direction of 28.1 degrees north of east. Final answer. For this next problem, I want you to realize it is extremely similar to that problem number 2 on your most recent homework assignment, 4-3. But we'll do this example to try to give you more practice. In this case, we have a motion in 2 directions problem where a football is thrown due south at 30 meters per second from the 50-meter line. At the same time, a gust of wind blows westward, meaning toward the west, across the field at a constant speed of 10 meters per second. And it wants to know what is the resultant football velocity and in what direction, degrees. Well, if you were to draw a picture of this, there's the velocity vector for the football that you've thrown at 30 meters per second. And then because the wind is westward, actually, if that is thrown south, then I need to show that like so. And there's now a westward direction blowing toward the west of 10 meters per second. I tried to draw it the same proportion, but you can see that this is not 3 times the length of that. But as long as you get the idea that one is larger than the other, you should be okay. I'm going to write in my values here. 30 meters per second due south and 10 meters per second due west. Before I go any further, what I'd like to do is draw in what the resultant vector looks like. It should be something to the south and to the west. And now it's my job to determine what that resultant magnitude is. Well, I see here that because they are perpendicular to each other, I can use the Pythagorean theorem to solve for that magnitude. And if you do that, you should have 900 meters squared second squared plus 100 meters squared second squared, and take the square root of that, you get a velocity of 31.6 meters per second. That is the resultant velocity of the football as you throw it due south and the wind also carries it at the same time due west. Now, just finding the resultant velocity is not enough for us. We also need a direction. And what I want you to realize is the direction is always going to be given from some particular axis, and it's always convenient to start that resultant vector on some XY axis system. So if I want to make this measurement from north, I can report that by doing this and realize that this is 90 degrees and that is 90 degrees, and I only need to find this angle in between there, and I can just add it to it. So let's go ahead and do that. I can use trigonometry to find this angle in between. I know all 3 sides, so pick your favorite function, whichever one will help you. Again, I'm feeling tangent. It's just my favorite function today. So for this angle theta, tangent of that angle is equal to the side that is opposite 10 meters per second divided by the side that is adjacent to it, which in this case is 30 meters per second. I run that through my calculator and I get 0.3, but that's just the tangent of that angle. I want the angle. So to get that angle, I take the inverse tangent, which is second function tangent of 0.3, and I get an angle of 16.7 degrees. Now that's not my answer necessarily, that's just this angle in there. If I want to report this answer correctly, then I would need to report it by having 16.7 degrees plus this 90 degrees, plus that 90 degrees. And what I end up getting is a total angle of 196 degrees, 196.7 degrees from north. That is my final direction, and this is my resultant velocity. Together, they make my final answer for this part of the problem. Now, in the next part of the problem, it says the football hits the receiver at the goal line, the 0 meter mark. We're telling you something here. If you are at the 50 meter mark and the football is received at the 0 meter mark, then that tells you in this direction, in the southern direction, the ball has traveled 50 meters. And you can draw this as a displacement vector. Remember, because the wind is blowing, you are also going to have a displacement in the horizontal direction. And that's what you're looking for. Because it's horizontal, I'm going to label it as d little x. And because this is vertical, I'm going to label it as d little y. And my resultant displacement in this case is going to look very similar. In fact, it is going to look exactly like the triangle that I used for my velocity vectors. But keep in mind, because these are velocity vectors, you cannot put them on the same triangle as these displacement vectors. Well, here's what you know. If you realize that the football is being thrown in the southern direction with a velocity of 30 meters per second, and I'm going to label that as the velocity in this vertical direction, I can use this information to find how long it takes to reach the receiver. If that's the case, 30 meters per second at a distance of 50 meters, the time that it takes for it to move downfield is independent of the time that it moves across field, is independent of the time it takes to go this entire length. It has to reach this point right here at the same time. The time that it takes to cross that horizontal plane is the same no matter what. So if I can use this information to solve for the amount of time that it takes for the ball to reach the goal line, then I would have my answer for how long it takes the ball to reach the receiver. Keep in mind this equation, which says the velocity is equal to the distance an object travels divided by its time. But in this case, I want to make it a little bit special. I'm going to add my subscript to show that it is my velocity in the vertical direction and my distance in the vertical direction. I'm looking to solve to get this guy all alone, and I can do that by switching these two. I end up getting an equation that looks like time is equal to displacement in the y direction divided by my velocity in the y direction, which is 50 meters divided by 30 meters per second, and I get a final value of 1.67 seconds as the time it takes to reach the receiver. In the last part of this problem, it wants to know, in relation to the thrower, how far westward is the receiver when she makes the catch? Okay, so keep in mind, again, on this football field, the ball is initially thrown from the 50-meter mark. And because it's thrown due south with a velocity that is westward because of the wind, then this football ends up getting thrown toward the southwest. If that's the case, then what you want to know is, what is my displacement in the, it shouldn't be the vertical, it is the horizontal direction. Well, you already know the displacement in the vertical direction. It's 50 meters because you go from the 50-meter mark to the 0-meter mark. What you don't know is this. You do, however, realize that the velocity in the vertical direction is 30 meters per second, and from that, you found it took 1.67 seconds to reach the end zone. If it took this long to move in the vertical direction, it will also take that long to move in the horizontal direction. Remember that the wind was blowing at a speed of 10 meters per second in the horizontal direction, and you can use that to solve for the displacement in the horizontal direction. The very similar equation looks like this. The velocity in the horizontal direction is equal to the displacement in the horizontal direction divided by the time. And remember, you found that time. It's the same time that it takes to move in the vertical direction. So if you throw that in, and take this value for your velocity in the horizontal direction and throw it in up there, you can multiply your velocity in the x by your time total to get your resultant displacement. In this case, it's going to look like 10 meters per second multiplied by 1.67 seconds, and that will give you a resultant displacement of 16.7 meters west. And that's your answer. Alright, I hope you're in good shape for the quiz.